A high-velocity bullet strikes a block of translucent blue solid. The material absorbs the kinetic energy without shattering. This is silica aerogel, the lightest solid on Earth. It is 99.8% air by volume. A piece the size of a person weighs less than a kilogram. It is often called frozen smoke due to its appearance. Production begins with a sol, a colloidal suspension of liquid precursors like tetraethyl orthosilicate, mixed with water and catalysts. Hydrolysis replaces the ethoxy groups of the precursor with hydroxyl groups, creating reactive silanol molecules and ethanol as a byproduct.
In the condensation phase, silanol groups react to form siloxane bridges, creating a three-dimensional network of silicon and oxygen atoms. As the network spans the entire volume, the liquid turns into a gel, a semi-solid state where the matrix traps the solvent. The gel must age for several days to allow further condensation, which strengthens the neck regions between the interconnected silica nanoparticles. During aging, syneresis occurs as the gel slightly contracts, expelling some solvent, while the internal covalent bonds continue to form. Before drying, the original water and ethanol mixture is exchanged for a more suitable solvent, like liquid carbon dioxide or acetone. Normal evaporation destroys the delicate nanostructure because surface tension at the liquid-gas interface exerts massive capillary pressure on the pores. Capillary pressure is inversely proportional to the pore radius, meaning the tiny nanopores experience forces strong enough to crush solid silica. To prevent collapse, scientists use supercritical drying, which bypasses the liquid-gas phase boundary entirely by increasing temperature and pressure. Above the critical point, the fluid becomes a supercritical state, where liquid and gas are indistinguishable, eliminating surface tension completely. Carbon dioxide is preferred because its critical point is reachable at 31 degrees Celsius and 73 atmospheres of pressure. Once the fluid is supercritical, the pressure is slowly released at a constant temperature, allowing the gas to escape without forming a meniscus. The result is a dry, solid block that retains the exact volume and intricate nanostructure of the original wet gel. Under an electron microscope, aerogel looks like a chaotic pearl necklace, with silica spheres between 5 and 20 nanometers in diameter. The air pockets within this structure are incredibly small, preventing air molecules from moving freely, which is the key to its insulation. The blue color arises from Rayleigh scattering, where the tiny silica nanoparticles scatter shorter blue wavelengths more effectively than longer red ones. This explains why aerogel looks blue against dark backgrounds, but casts a yellow or orange shadow when light shines through it. Silica aerogel has a thermal conductivity as low as 0.013 watts per meter Kelvin, lower than still air. The Knudsen effect occurs when the pore size is smaller than the mean free path of gas molecules, drastically reducing gaseous heat conduction. In open air, molecules travel 70 nanometers between collisions. In aerogel, they hit a wall after only 20 nanometers. Because the pores are so small, air cannot circulate within the material, effectively eliminating heat transfer through convection. Heat conduction through the solid silica is also low because the path is incredibly tortuous and the contact points between spheres are minuscule. At high temperatures, radiative heat transfer becomes significant. Scientists add opacifiers like carbon or titanium dioxide to block infrared radiation. A common demonstration shows a delicate flower sitting on a slab of aerogel while a blowtorch blasts the underside without wilting the petals. Despite its lightness, aerogel can support thousands of times its own weight in compression due to the distributed structural network. Mechanical properties like Young's modulus scale with density raised to a power, typically between 3 and 4 for silica aerogels. Aerogel is notoriously brittle. While it survives high compression, it has very low tensile strength and shatters easily if bent. In ballistic applications, The aerogel dissipates energy by undergoing massive local crushing, converting kinetic energy into a massive increase in surface area. The National Aeronautics and Space Administration used aerogel in the Stardust mission to capture particles from the tail of comet Wild 2. Comet dust travels at 6 kilometers per second. Aerogel slows these particles down gradually without the heat of friction destroying them. By capturing the dust gently, scientists were able to study pristine organic compounds from the early solar system for the first time. Alumina aerogels are used for extreme heat environments, resisting temperatures up to 1200 degrees Celsius without melting or collapsing. Carbon aerogels are created from the pyrolysis of polymer precursors, resulting in a black material that is electrically conductive. These materials have a specific surface area of up to 1,000 square meters per gram, ideal for high-capacity supercapacitors. Their high porosity allows for massive ion storage at the interface, enabling batteries and capacitors to charge and discharge almost instantly. Graphene aerogels have pushed the limits of density even further, being 7 times lighter than air by using ultralight carbon sheets. Recent research involves cross-linking silica networks with polymers, creating a composite that is significantly more flexible and durable than pure silica. These reinforced aerogels are produced as flexible blankets used to insulate subsea pipelines and industrial equipment in confined spaces. Most aerogels are treated with silanizing agents to replace surface hydroxyl groups with nonpolar methyl groups, making them waterproof. Because they are hydrophobic but oleophilic, aerogels can absorb up to 90 times their weight in oil while repelling water. The massive surface area makes aerogels excellent supports for catalysts, allowing for faster chemical reactions with minimal amounts of expensive metals. Physicists use aerogels in Cherenkov detectors to measure particle speeds because their refractive index is perfectly situated between gases and liquids. By controlling the density during synthesis, the refractive index can be tuned between 1.01 and 1.05. Aerogel is being integrated into the layers of next-generation spacesuits to protect astronauts from the extreme temperature swings of Mars. For liquid hydrogen and oxygen storage, aerogel insulation reduces boil-off rates by orders of magnitude compared to traditional foam insulation. The primary barrier to widespread use is the cost of supercritical drying, leading to research into ambient pressure drying techniques. By chemically modifying the gel surface to be highly springy, the structure can collapse during drying and then pop back out when dry. As production costs fall, aerogels will transform architecture, providing translucent windows with the insulation value of a thick brick wall. From stopping bullets to catching comets, this solid smoke remains the peak of material science and chemical engineering.